Yeah, the weight is really what
Of course, labor laws do kind of screw over companies in that respect because they have to pay you for the time that you're on call.
Yeah, if you're an agent, it's not. That makes sense.
Well, I was asking because we covered the last half of I was the first person. Did I miss something?
I love the little inserted courier font name at the top.
Yeah, well, everybody keeps forgetting their name.
Oh, the mole highway. I'm just struggling.
Are you thinking of applying for the position at Alpha Zeta?
Oh no, I'm not gonna apply as an officer for Alpha Zeta Pi. Absolutely not.
Me too. No, that's a lot.
I am too busy to take on that kind of a responsibility. I'm already busy enough as it is with music club.
Yeah, I mean, you're president already.
I have cemented my position in student government and I am good where I am.
So are you still gonna continue?
Oh yeah. I'm gonna
You're
do
gonna do it since
I'm gonna do music club until I graduate.
But how are you gonna like cope with CNA?
Carefully and with great determination.
While also taking a 16 credit loan?
Carefully and with great determination.
Good luck.
How goes it?
Flying by.
Yeah,
I'm
it
like-
really is.
Scared it's like week 8. Like, that really is scary.
I know, finals are almost scary. That scares me.
Yeah.
I think I'm gonna go to the study cafe this year, but I don't know if I'll be busy or not. Music department is doing toe tapping Tuesdays today at 2:30.
Oh, cool.
If you're interested, you should stop by 132.
I would if I didn't have lab.
How late are you going?
Probably the usual time, 1:30 to 4:20.
Oh yeah, this lab.
Yeah.
I forget that you have 2 lab blocks.
I read it.
Oh my gosh.
I actually remembered to bring my computer charger today. Thank God.
That's good.
Well, hopefully you hear us playing from down there. You probably will. The sound carries really well in this
Oh,
building.
I've heard compliments already. Yeah.
I really hope we're like not too loud because oh my God.
Carmen had a radio show. That's curious.
Yeah.
We're all just really cozy in this HEC building. That's how I like to think of it.
We're bugging you guys. Please make it known.
Not me personally in other classes, but I've just heard things.
Oh yeah.
Yeah, it's a seasonal.
Well, they can reach out to Dr. Sai or us and let us know, hey, don't do that. We will
What are you
stop.
gonna do? Don't practice. Like, it's just everything carries up. That's what I said. It's just the realities of being in this building that and Redwood does not experience those same.
Yeah, because they have their own spaces for the arts there.
Like, everybody has a separate building.
It helps.
Yeah. I'll stop talking.
Why?
What's this thing about the cost of building maintenance to have a separate building and the student population difference?
Yeah.
It bothers me.
we can do all of this in such a compact area. You know, I think that's why they cut down on all the buildings here in Medford, because there used to be the one across the street over there.
Yeah.
Then I think there was one over by the library. I think there was one down the way somewhere.
Yeah.
When they cut all of them. And it was during COVID that they did it.
Yeah.
But it made sense. Should have. I remember coming into a writing class here during COVID, and the building just completely empty, except for a few people.
Of course, that was COVID.
Yeah. I just knew it was crazy though.
No, I actually just like the setting. It's like 2 nights in a row. But at that time, it's like I got some. I had some tea like most.
So that was like they were actually
Maybe that. Not the research paper, but the same thing. We just prepare short summary of the 10 seconds. For the web. Yeah.
Yeah, yeah. I can get that.
Yeah, you know, I hate 30 Zoom class.
Make sure you want to.
I know I talked to him like
Actually, like last did yours take forever too? We took the whole period. Yeah. So
now
I guess
I just focused in, and then final will be easier since I switched to 201.
Oh, you didn't do this. Yeah, no, I did.
Yeah,
I did
so
last week.
so my treatment
I do. Which I did on Wednesday. Just because that's like the way my schedule works out.
and so I went
Like,
into the trio again.
all the
Thank
curriculum
you.
and the formulas.
I talked to the advisor on the
I don't know if I called him. What's up?
yeah, but
Anyways, that.
Dusty said that he was able to drop out.
Yeah, I did. Most of it seems pretty straightforward. It's just some of them. The plus and minuses. Yeah, I like
It's actually 10 a.m. That was
but yeah,
I have a stapler.
What?
Yeah, I don't have a hole punch on me.
yeah.
You
It's like,
need it?
Oh, come on.
yeah, when my calc test, I got 38 out of 45. But
I'm gonna take statistics.
there was one that was you said you need to take out those, right? So it was basic motion.
All right, let's get started.
Sign over X.
So happy Tuesday. And then I can't believe it's already week 8. So let's just kind of look at our schedule to see what we have going on. So we're looking again week 8. So we're going to be doing our empirical formula lab today. So we will be having an open flame. So hopefully you'll have your cotton clothing. Otherwise, come on Thursday with cotton clothes. And then so looking into next week, again, we're kind of shortchanged a day with Thanksgiving, so we only have the Tuesday, and then due to that, we'll have no lab next week again there. And so next Tuesday is again another good opportunity to do makeup, any things that need to happen, or again, just more tutoring sessions. So I'll say, so no lab next week due to Thanksgiving. And like I said, we'll only have class on that Tuesday. So kind of crunch the solution chapter, but that will be okay. Other announcements. So you probably have seen the advertisement going around. Tony arranged for a speaker. So I don't have the poster on me, but I decided I'll offer some bonus points. So let's do 5 bonus points for the speaker. And so it's going to be this Friday at 1 p.m. Again, I would check the poster. I can email out or post on Blackboard more details. But if you can't make it, it should be live stream on my YouTube, so you can catch it later. And then all I'm asking is to write 1 or 2 sentences about the speaker. So anything that was cool, what you learned, or just anything, any thoughts you had. All right, and then, so I'm trying to kind of revive Earth Club, and by Earth Club, I secretly mean Science Outreach Club. So I kind of inherited Earth Club when I joined here, and yeah, I mean, we used to do a lot of wonderful hikes. Last year, though, we started doing this kind of Boys and Girls Club outreach. I don't know if y'all are familiar with the Boys and Girls Club program, but we had a nice group of volunteers that were going there about once a month to present activities, and then that's kind of stopped, but I'm trying to revive Earth Club, and so I believe my president is back in action. So if you happen to know Link Baldwin, that's who's in charge of the club. But we need other members to go out, especially if we want to revive this Boys and Girls Club outreach effort. We were going twice a week, so we had 2 groups, but by twice a week, 2 different locations. So I believe it was Talent and Phoenix. And so that's a good activity, but I mean, this is a club, an RCC club, so it's really open to the possibilities of whatever y'all want to do with it. That's why it's kind of like Earth Club in name, but then people were way more interested in doing like science outreach, and I never rebranded it as Science Outreach Club, so that's something to think about. So you can also email me or talk to me. I have a lot of ideas on the back burner with this, but I just kind of need bodies, especially we could also think about like collaborating with SOU's club and maybe trying to do like a CHEM club collaboration, since I do have a professional ACF membership, and so we could kind of think about how to take advantage of that and become an official ACS club. But again, just kind of things to think about, opportunities, so let me know if you're interested in that. Trying to think if there are other announcements. Yeah.
Who did you say the speaker was?
I didn't.
Okay.
I forgot her name.
Okay.
It's some doctor. Yeah, it's going to be streamed though.
Okay.
But yeah, otherwise it's this Friday. The posters are all around.
Okay.
I haven't read them, admittedly. And so then the other assignment that I wanted to talk about is our mini writing assignment. So kind of our preparation. And so our writing assignment is really a research article summary. So I'll pull up the example. So you guys have a handout. So let me pull up, lost my windows here. So I gave y'all an updated copy, but I didn't post it to myself. So basically we're kind of looking at where our project is going. So just kind of put ourselves in context, right? We've been practicing writing these little abstracts, just trying to get our writing skills going. But eventually our goal is to write a whole research paper on whatever topic we're interested in. Again, I'm keeping it open to whatever topic you're interested in, so you can pick something that's like relevant to your field and get really into it and actually be excited about it, as opposed to dreading the assignment. And so we're just going to start researching topics that might be interesting. And so this quarter, that's what you're asked to find is, it says to pick a journal article. I'm not opposed to you looking at several and maybe like kind of summarizing them if you feel that's kind of more appropriate. But I'd probably focus on just kind of one article and then focus on summarizing that. And of course, you can always reach out to me, or if you're really having difficulties, you can use a previous journal article. Or again, I don't really suggest that, though. I would have some fun with it and start diving into whatever your area of interest is. And so I didn't put a due date, but it'll be due our last week, or ideally, the sooner the better. And so we just want to do about 10 sentences. Sorry, I updated this because it didn't make much sense. So we want to do about 10 sentences, and I fixed the spelling, sorry. And so kind of an example of this, let me pull up the article. And so this is an example of a summary of a research article. And so here's the research article in question, and I'll probably need to download it and you guys can read it just to get an idea. And so it's a kind of dense paper. It's about flipping stereo centers. And then again, you can just see how dense this paper is. We're not going to go over it right now, right? That's not the topic of today's lecture. But just appreciating how you take this nice long paper and then this author, put it in a much more succinct summary. So that's our goal, right? Find a paper, pick it. You want it to be a primary research paper, right? So you don't want to do a review because that's already a review. So a review article, though, that can be good for gathering background information. But again, for your research article, you really want to hone in on some primary research going on in whatever experiment. So focus on a specific experiment, and then you'll practice reading it. So that's always good skills, right? Reading the scientific journals and then summarizing it. And then, of course, you will probably run into paywalls. I expect that. So that's why I start this early. And then, of course, just email me if you run into a paywall. And I will attempt to get around it. So like I said, I have a lot of journal access still thanks to my old graduate institution. And luckily my login still works. But that doesn't mean that I have access to every single thing. But like I said, I usually can get some, or I can pay for them because I get a certain number of articles with my professional membership as well. So sometimes I can buy them for free. All right, does that clarify the assignment? And again, feel free with the topic. If you're worried that your topic is a little too far from chemistry, just check with me, but chemistry is pretty adjacent to anything, so I think we can kind of stretch a good topic, but you just really want to focus in on kind of the chemistry part of whatever question you want to look at as well. All right, questions? And then I'll try to hand back papers. I'm still just like a tad behind on grading. So I've graded a lot of things, except I still didn't quite finish all the flame tests and like spectrophotometry labs. So don't panic yet, unless it's one of the earlier labs. So I still have some like homeless like lab 2s that haven't been claimed. So if you're missing a grade still, you might want to bug me. Just keep an eye on those grades so we can get them fixed for the end of the quarter, so you have accurate grades. All right, I think that's all the announcements. And so now we're diving into chapter 11, which I think is a nice, fun topic. So now we're talking about a mole and figuring out how to express and communicate right quantities of reactions. And so let's first define, well, what is a mole? And so what is a mole? Does anybody have any ideas?
It's a certain amount of protons or something, or like atoms.
So yeah, it's a certain amount of atoms, and right, I'll just kind of put that right. We have a defined amount. And it's really just like a baker's dozen or some other arbitrary unit of measurement. And so how they got to it, let's do a mini derivation here. And so they wanted to base it off of carbon. And so basically they said, okay, well, one atom of carbon, and now we're just looking at one that has, right, our carbon 12, so our main isotopic abundance. And so that corresponds to, and this is roughly, so I'm just kind of doing estimations right now, but roughly 12 atomic mass units, which if we were to convert that into grams, so that would come out to 1.999265 times 10 to the negative 23rd grams. So again, right, this is one atom of carbon. And then we want to say, well, what factor, so some conversion factor, which is going to end up being Avogadro's number, but, right, so what conversion factor then sets it to that 1 mole is defined as 12 grams per mole? And so, right, we could do a little, like I said, it'll be a little off, but we can roughly see where our number comes from. So, right, divide 12 divided by 1.99265 times 10 to the negative 23rd. And what do we get? So 6.022 times 10 to the 23rd, which is right roughly the accepted value of Avogadro's number. So now we see kind of where it came from. So again, right, we got our conversion factor, 6.022 times 10 to the 23rd, and Avogadro's number. And again, all this is to say is a mole is our macroscopic amount. So we're trying to figure out how we can, on a relatable scale that we can all kind of talk about, define, right, what is a mole, what is a molar amount, and again, having quantities that we can kind of weigh out and talk about. And so then we're just kind of defining some things. And I think we kind of mentioned it before, but now we're just kind of re-emphasizing it. And so this is why it works out, again, nicely on the periodic table. So all this is done on purpose, right? So that way we can go to our periodic table, we can look up any element, and then, right, this is our average atomic mass, either in atomic mass units or in grams per mole. Again, thanks to our conversion factor. And so that's just emphasized. Again, we can add up all our weights, our average atomic weights. And so water, we would again get that one individual molecule is 18.02 AMU, and then 1 mole of water has a molecular mass of 18.02 grams. And again, you want to make sure that we're emphasizing that it's right, grams per mole here is our unit. And so now we can start to convert these things. So now we want to convert 35.55 grams of carbon to moles of carbon. And so you might want to practice just kind of setting your conversion factor. So from our periodic table, again, we can just look at our molecular weight of carbon. So it says 12.011. So again, that's our average atomic mass in grams per mole. So right, we're saying 12 grams is 1 mole for carbon there. And so that's our conversion factor. And so this should feel pretty similar to our first chapter, our first 2 chapters of just converting metric units, so same sort of thing. So set up your dimensional analysis, so 35.55 grams. And then we want to divide it, right? And again, this is just our ratio, so we're saying there's 12 grams and 1 mole. And so if I want to find moles, I'm going to flip my conversion factor. Moles goes on top, 12, and I'll use 12.011 grams to be more precise. On bottom, and then just have your calculator. So I'm just going through it. And so I'm going to base my answer off of 4 sig figs from our problem. So 3.55 divided by 12.011. And so we get about 2.95 moles. So then let's write that to 4 sig figs. So 2.9. Oh, and then rounding. So that rounds up. Oh, that rounds funny, doesn't it? So sorry. So 9.597. But then I want to round it to 4 sig figs. So 2.960 for 4 sig figs. And moles. Does that make sense for the first one? Pretty straightforward, right? Should be pretty simple. So try the next one. So then how much do 0.227 moles of silicon tetrachloride weigh? And so, right, you might want to first get the molecular weight of silicon tetrachloride, get your conversion factor. So I'll give you all a minute or 2 to work that out. So what do we get for the molecular weight of silicon tetrachloride? Let's start with that. Any guesses? Yeah, what'd you get?
38.57.
Is that just for silicon or?
I got that as well. I might also.
38?
38.
As the final, not the molecular. Yeah.
Oh, as the final. Oh, my bad. Yeah, y'all are right. Sorry. But, okay, so walk me through it. So start with the molecular weight, though, of silicon tetrachloride. So 169.898. Sorry, I wasn't staring at my own answer. I was looking. All right, perfect. So then we can set up our dimensional analysis. So moles. And then this time I'm going to plug it in with 169.898 on top for grams. And then moles cancels. And so, yeah, you had said 38 point what?
597.
So 38, and I'll round it. So we only have 3 sig figs here, so 38.6 sounds like. Good. And so don't forget that this is also a good place to do proportions. If you like proportions, again, whatever feels good to you mathematically that's comfortable. I'll just kind of show a different setup, right? Again, you can set up your ratio. Well, I know that 169.89 grams is 1 mole. So then you could set up your proportion of X, right? X grams is equal to 0.227 moles, right? Moles with moles, grams with grams, cross multiply and divide, and you get the same thing mathematically, right? So just showing you different ways to see it. So again, whatever works, right? Just practice it. So hopefully you saw that with the last midterm. Is I'm not trying to force you to memorize a bunch of stuff. It's just, can you do it, right? Do you remember how to execute it? So you want to just practice and become comfortable. All right, so let's try this one. And so, right, a lot of chemistry too is just kind of puzzles. So let's see what we have here. So it's asking for how many molecules of aspirin are there in 30 milligrams. So start with that. So I'll give you all a few minutes. But then you can start thinking about how would we approach atoms of carbon, right? What conversion factor can you make for that? And oxygen. So let's kind of check in and see how far everyone has gotten. So what are good pieces of information that you might need? So we're given our formula here. So what probably do you want to start with? Mass. So right, so what do we get for our molecular weight then of aspirin? And right, we just have to add this up. So do we all know how to find the mass of this? So again, ask questions. But so roughly, so 12.011 times 9 plus 1.008 times 8 plus 15.99 times 4, or something like that. So that's what I get for the molecular weight. Is that what other people got? Okay. Excellent. So 180.159. Again, that's grams per mole. And so we could do a few different kind of tricks here. So we, of course, so first you have to convert, right, 30 milligrams to grams, so 0.030 grams. And so you could have gone on here and found moles, right? So we could have, I'll call this dimensional analysis. And so we could start off kind of more formally, 0.03 grams, convert it to moles, so 1 mole, and then multiplying it. So if we want to go from moles to molecules, so 1 mole is 6.022 times 10 to the 23rd. So again, that's atoms or molecules. So that would be one way to do it. And so you can tell me what you got. You can also do, again, some little, right, tips and tricks. So if we know this is a mole, right, we already know that 1 mole is equal to 6.022 times 10 to the 23rd. Again, in this case, molecules. So we could have also set up a proportion. So you could have set up 180.59 is, again, Avogadro's number. Molecules. So then you want to figure out what 0.03 grams x. So right, that just kind of helps you skip a little step, right? You're still just using relationships and conversion factors. All right, so then what do we get when we plug this in? So either way, we should have the same answer. So let's hear it. Plug it in. And then just make sure you can enter it in properly. I would be using the exponent. So what do we get for our answer then?
2.8 times 10 to the
2.8.
18th.
I might double check that because let's see. Did you convert the 30 mgs to 0.03 grams and then divide by 180, multiply by 6.022? What do other people get?
1 times 10 to the power 20.
So 1 times 10 to the power of 20, and so that's molecules. So that's what I get with the calculator. Did you figure out?
Yeah, what I did wrong there.
So yeah, calculator, typos. And we only have one sig fig, so it's kind of awkward. All right, so then let's look at our next half of that problem. So then it asks how many atoms of carbon, how many of oxygen. And so now what do we need to do? What does our formula tell us? What conversion factor can we make? What does our formula tell us?
I think we still need to use the Avogadro's number and multiply it with the number of, with the mass of the atoms.
Could you just replace, like, instead of the total number, like, all the same in the formula, but just replace the total number with, like, the total amount of oxygen or something?
Yeah, so you mean, so I would just write it out, right, that we have, for every 1 molecule of aspirin, so C9H8O4, that means we have, so in this case, if we're looking at oxygens, so we have 4 oxygen atoms. So, right, they're basically in a 1-to-4 ratio. So that would suggest that we have, right, 4 times 10 to the 20 molecules of oxygen. And then, yeah, so for carbon, right, same thing. So 9. So that would end up being, so we have 9 carbons for every 1 molecule of H8O4. And then, so I think, Happy, you were kind of suggesting a different method. So did you find like the percent composition maybe? Is that what you did?
Mm-hmm.
So then you found like what percent oxygen was of the total?
I didn't like calculate it. I just wrote it and didn't write the answers.
Yeah, I mean, it's not wrong, right? It's just another way to get to it. So that's like the fun thing about this kind of unit is it's all kind of a trick. So again, we could start over. So we have 30 milligrams of our C9H8O4, right? Maybe you want to figure out your percent weight. That would be another way to do it, of oxygen. So if we said we had 180.159 total, and then, so let's start by oxygen, just as an example. So oxygen, so 4 times, would be about 64 there. So let's get the exact percentage. So divided by 180. So then, right, we could find that we have 35.5% weight. So this is weight per weight. So this will help us with our next unit. But just basically 35% by weight calculation of oxygen. So then you could go on to figure out, right, your total mass of oxygen and then calculate it that way. So let's compare. And so now I'm just kind of going through it. So then if we have 0.03 grams, so times 35%. So that gives us 0.01065 grams. And again, now we could do if we want to figure out how many moles of oxygen, and we have 16 grams per mole. Whoops. So divided by 16. So then that gives us, right, how many moles we have of oxygen. So 6.65. And notice, right, we're just talking about individual atoms of oxygen, so that's why we're using 16 as opposed to 32, right? We're not talking about diatomic oxygen right now. And then multiply it by Avogadro's number, 6.022 times 10 to the 23rd. And, right, we get the same answer back out. So then times, let me just finish writing that down. So moles of oxygen times 6.022 times 10 to the 23rd. And again, back to the 4 times 10 to the 20 atoms there. So, right, so that was good, right? So 2 different methods, so it doesn't really matter how you get there, as long as your conversion factors all work out, right? You'll get to the same point. So I find that rather comforting. Questions about those? And so like we're seeing, and this was also kind of teased out, and we were reminded of this, right, with how they found the periodic table and all the ratio of elements. Well, that is part of this law of the composition of compounds. And so we found that our chemical formula is in relative quantities, right, of each element. So again, they're defined chemical quantities that translate out to this formula. And so we can also find, of course, the percent in each element. So I think we've kind of done this before, but now we're kind of going to take it a step further. And so, of course, we can figure out our percent mass of any element. Obviously, we've done that before, taking our total molecular mass of whatever element we're interested in and dividing it by the compound. And then always write a little bit of error from rounding. And so then eventually we're going to work on also determining how to get a formula from our experimental data. And so we're going to work on getting our empirical formula, which is just defined as our simplest whole number ratio of atoms in our elements in a compound. And so this is super important, actually. And like, it seems really simple what's going on, but this is actually a very high standard of purity. And so this technique, elemental analysis, it's used to give your percent composition. And so, right, your masses are reacted. In retrospect, I should have gotten like a paper or something. I'll find a paper that shows this so you can actually see it in action. But basically, your elemental analysis has to be within a certain range, and it has to be extremely pure, I know from experience, because elemental analysis is the hardest thing to get to be accurate. But that's how you know that you made what you made. And if your elemental analysis is not hitting, that could suggest some impurity, which that's happened in the past, where I believe they got like manganese and iron mixed up. And if you look right, they're right next to each other. And I believe they were trying to add iron, but their sample was impure enough that they actually made a manganese compound. All right, so we'll walk through this process together. But let's actually, this is probably a good spot for break time. I know it's a little early, but we're about to get into all this process. So let's go ahead, let's take a 10-minute break here before we get into our empirical formulas. So try to be back around 11:50-ish, and I'll hand back some papers, and we'll look at this.
So just to make sure I have this clear, to get the oxygen, you just have to take the average of oxygen in the aspirin, and then that gives you this number, and then you times that by the Avogadro's number to get the moles of oxygen.
Yeah, that's another way to do it. Otherwise, we could have just gone from our ratio, because we had however many, we found how many molecules,
Yeah, it
right,
was
of
40.
aspirin,
Yeah.
or the 1 times 10 to the 20, because that was molecules of aspirin, so then you just multiply it by 4.
Okay.
So that's another way. But yeah, either way, they give the same answer.
So I will be here on Thursday to play volleyball here for RCC, and we're going off to our championship.
Oh,
And
nice.
So, yeah. So I won't be here on Thursday. I know I'll miss the lab, but is there any important?
I mean, there'll probably be like a quiz, but you can make that up.
Okay.
Yeah, and then you can make up the lab on next Tuesday if that works.
Yeah, that works. Okay,
Okay.
cool.
I missed last week.
We didn't
Okay.
end up doing because.
Will someone take that job?
It should be in the grade. Okay, well let me look because it should have been returned.
No, I have it up to 3. I have the other ones due before I know I didn't give to them.
Yeah, well I'll look
Okay.
because, yeah. So, I'll work on it. I'm kind of working on it.
I'm zooming, so
Okay.
I didn't want to come in late.
That was the doctor's guy's office. I think I can use it for a really long time. You really should. It's gonna be cool.
I was wondering if you had week 2 lab. Any no names?
Yeah.
I just checked that I have a grade.
Those are the two I see. At least right now. Are any of those yours? Okay. Well, I can look around. There's more piles. So those aren't yours. Okay. Well, I'll look for others with no names, because there might be more. We got come see me, like in office hours and lab.
Do you know any chance if I got it back? Or, like, not saying, like, if I got it back and there just wasn't a great fit.
I mean, that's totally possible that that could have happened.
Okay.
So I would double check your stuff. All right, do we all make it back? All right, so I wanted to show what this actually looked like in a paper as well, which was easier said than done. So this is just a paper that I pulled from the group that I used to work for. So this is about CO2 reduction with these fun-looking compounds. But basically what we want to focus on is anytime you make a new compound, you have to prove that you made the new compound. And so every journal has different standards. So you can see this is what like an actual prep looks like. So right, it's much more succinct than something that you would read right in your lab where it like tells you everything like get this glassware. So that gives you a sense of how a real synthetic procedure works. And then, so then eventually you have to characterize it. So this was their first compound that was officially characterized 1 and blah, 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 NMR data, which is wonderful. You'll get there when you get to OCHEM. But what we care about is this little bit right here. So this is what it's referring to, elemental analysis. And so you plug in this formula so you can use a standard chemistry program like ChemDraw, and it'll calculate it for you. So this is the percent of carbon that it's getting back. So it would be 57% carbon, and then it came back with 56.89. And so depending on every journal, they publish like what the accepted window of error is and what has to hit. And so elemental analysis usually just gives you carbon, hydrogen, and then nitrogen if you have nitrogen in there. All right, so let's go through our math here, since we can also, like I said, use these results to back calculate what our formula is. So let's go through this together. So these are kind of our procedures and how we'll approach every problem. And so when you want to find your empirical formula, so first we'll convert any percentage to grams. So right, sometimes they might just give you, okay, it's these percentages, blah, blah, blah. And so if we're not given a gram amount, we can always just assume that we start with 100 grams, right? That makes the math kind of easy for us. So if we were given 24.5% carbon, we can just translate that to 24.5 grams of carbon. And then once we get our starting mass of grams, then we'll convert those mass amounts to moles. So just dividing by the molar mass of each element. So again, carbon, hydrogen, or oxygen, or nitrogen generally. And then we'll divide by the smallest number of moles to obtain our mole-mole ratio of our elements in our compound. And then this is where it kind of turns into a judgment call, and then also kind of experience and trying to figure it out. So if our number is within 0.1 of a whole number, we'll try to round. Otherwise, we want to multiply all ratios to kind of make it a whole number ratio. So, right, if you have 0.5, try to multiply it by 2 to get a 1:2 ratio. If it's 0.3 or 0.67, right, multiply by the appropriate amount to try to, again, make a whole number. But let's go through this all together. All right, so let's look at our problem. So it says that we have a compound that contains nitrogen and oxygen, and it's decomposed in our lab, and it produces 24.5 grams of nitrogen and 70 grams of oxygen. So it asks us to find our empirical formula. And so let's go through those steps. So again, step 1, get all percentages to grams. And so we're already in grams, right? They gave it to us, so that's kind of nice. So check. And so next step, find our moles. So let's go ahead and do that. So now we're just going to find our moles of each. So I'm going to start with nitrogen. So 24.5 grams. We can go to the periodic table. I'm just really emphasizing, right, that we pull this piece of data from our periodic table. Okay, there's our mass, 14.007. And again, that's grams in 1 mole there. So now we can figure out moles of nitrogen. And so then punch that into the calculator, and I'll keep at least 3 sig figs, so 1.749, or I won't round properly yet since we're not done. So moles of nitrogen. Then let's repeat that for oxygen. So, So same thing. So we're given 70 grams of oxygen to begin with. Pull up our periodic table. 15.999 grams per mole for oxygen. And so again, divide 70 divided by molecular weight of oxygen. So 4.375 moles. Okay, good. So are we all to here? All make sense so far? Speak now. All right, good. So then the next step is divide by the smallest number of moles. And so which one's our smallest? So nitrogen. So let's go ahead and do that. So we'll divide by nitrogen. So divide by smallest mole amount. So aka nitrogen. And again, I'll be really explicit right now. So 1.749 moles of nitrogen divided by 1.749. So obviously that's 1. Now let's repeat that for oxygen. And so that gives us a 2.5 ratio. So right, we're saying we have 2.5 moles of nitrogen for every 1 of oxygen. But then what do we notice about that? And what did it say that we want to do? Right, we need to make it whole numbers. So what should we multiply it by? Oops. Sorry, I wrote that backwards somehow.
You could multiply by 2.
Yeah, perfect. So multiply it by 2. So then we get 5 oxygens for every 2 nitrogens. And then this ends up being our empirical formula. So then we can guess that our formula is N2O5, so dinitrogen pentaoxide, which that is a real compound, so that seems fairly reasonable that we might get that. So that looks good there. And so what about the last little step? So again, we mentioned that this is really our empirical formula that we're finding. And okay, so let's look at our next caveat here. So it says that our empirical formula is a multiple of our empirical formula, right? So what is that saying? So it's saying that, again, our empirical formula is just our smallest ratio. But we're not really accounting for the true structure. And so it's a lot more easier if we talk about something that has a very different empirical and molecular formula. So let's say we were looking at benzene. So benzene has a molecular formula of C6H6. Of course, if you were doing the math calculation, you would have come up with an empirical formula of C1H1, right? So again, that would just be our ratios. But then we would need extra information. So, so to know the actual formula of the molecule, we have to have the molecular mass of the compound. And so this is determined by mass spectrometry. And so basically, you can shoot this down a mass spec, and then it gives you the parent peak, which is corresponds to your, of course, formula mass. And again, it should be in an integer relationship. So going back to this example, we would get our empirical formula, but then you'd get your mass for benzene. So then you could divide your total mass divided by your empirical mass to get your integer ratio there. But again, you'd have to have an additional piece of data. And so that's also just to show a paper. So going back to that same paper, let's see, they should have calculated our mass spec. Maybe they didn't. I was hoping for mass spec data. Well, so it depends on the journal and what you're trying to show, because sometimes they have different. Mass spec isn't always required. Let me find another paper. Oh well. Well, I'll find an example later of our mass spec. All right, so let's look at some more combustion analysis. So again, right, combustion analysis, elemental analysis, same thing. So again, very powerful technique. And so we get, again, our percentages of carbon, hydrogen, oxygen, like I mentioned, sometimes nitrogen. And then by knowing our mass and our composition of our elements in our product, then we can figure out our original formula. And so kind of the key is our combustion analysis that we're going to be focusing on is only going to be for organic compounds now in this technique. And so let's look at what we're starting with. So what's a combustion reaction? We covered it super quick, so maybe we forgot. But what are some characteristics of a combustion reaction?
Type of combination reaction where you have one product.
So it's not always just like a pure combination, because
Needs to be a presence of oxygen
so we do need oxygen. So I was looking for that.
to produce.
Needs to be high carbon dioxide and water.
And then, yeah, carbon dioxide and water. So good. All right, so now let's start to look at a couple of pieces of this. All right, so our carbon, right, any CO2 that is produced comes from our original organic molecule. So we can start to see, right, we can figure out how many moles of CO2, figure out how many moles of carbon, and that gives us how many moles of carbon we had initially. Same thing for hydrogen. So notice, right, all the hydrogen goes from your organic molecule and then becomes a water. So we'll have to deal with this 2 ratio there, so kind of watch that. But then the oxygen, again, we'll go through this process together, but it's a little tricky, right? Because like it was mentioned, well, we need oxygen, so we're adding in external oxygen to our sample, right? So this is kind of confounding, but I'll show you how we'll deal with that to figure out, right, how much oxygen was in our original sample. And so blah, 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 that kind of walks us through, but like I said, we'll go through this more detailed. And so this is just kind of showing you what a combustion analysis would kind of look like. And again, right, so to get your paper published, what you do is you send your little sample that's perfectly pure, and you seal it up in a vial, and depending on how sensitive it is, sometimes you have to pack it cold and all these sorts of crazy things so it doesn't decompose, because you have to ship this off to like a special lab to get it analyzed for. And so then they would burn it, and then, right, have these different absorbers that can, again, quantify the amounts of our water and carbon dioxide. All right, so let's try this one. And so first we're going to start off with a little bit easier one for a warm-up. And so this is slightly different and slightly easier in that we only have carbon and hydrogen, so that we don't have to figure out how much oxygen was added. So we have CXHY gives us CO2 and water. And so they gave us a gram amount, so 1.83 grams of CO2 and 0.901 grams of water. All right, so let's go through this. So the first thing we want to do, again looking at our setup, so kind of looking over here, right, we want to determine moles of CO2. So let's do that. So find moles of CO2, right, because we're trying to get moles of carbon. That's really what we're at, but one step at a time. And so let's do that. So 1.83 grams, and then divided by the molecular weight of CO2. And so let's just find that together. So 12 plus 15.99 times 2. So roughly 44 grams per mole for our CO2. So divided by 44 grams per 1 mole. So how many moles of CO2 does that give us? So punch it out. If you're online, I am watching the chat. So then do we get this answer? So again, I see some nods. So 0.04158. So again, that's moles of CO2. And then, right, we have 1 carbon in there. We could write this out if we really wanted to. So I'll kind of put it over here. So we have 1 carbon in every 1 CO2 molecule. So then this means we have 0.04158 moles of carbon, right? Does that make sense so far? Okay, good. And so now, just kind of remembering back to this step, right? We're just trying to get moles of everything. That's all we're doing. So, okay, we're back to moles. Let's repeat that for water now, right? We need to figure out moles of water, which will give us moles of hydrogen. We just, again, got to account for the little 2 factor. So now I'll set that up. So now find moles of H2O, and then that will give us H moles. Again, except we have 2 hydrogens in every 1 water molecule. So don't let the factor of 2 throw you off. So same thing, we'll start with our 0.901 grams of water. And then what's my molecular weight of water? 18.015. Love it. So grams per mole. Excellent. So right, just dividing. Hopefully this is, again, feeling good about the process. So now I have 0.05 moles of water, 0.0500 moles of H2O. And then, right, we have our 2 here. So now we need to multiply it by 2. So times 2, or I could set it up a little bit more formally, right? 0.055 moles of water, 2 hydrogens for every 1. So now that gives us 0.100 moles of hydrogen, right? Does that make sense? And so now we're back at the same step from earlier, right, where it says to divide by the smallest to get our ratio. So we can do that again. So let me insert some space here. So now divide by smallest number of moles. So let's see, we have 0.1 compared to 0.04. So it looks like we'll divide by moles of carbon. So I'll just put that, so carbon. So then obviously carbon's going to be a 1 ratio, but I'll still just write it out. So 1. And then for hydrogen, so we had 0.100 moles divided by our carbon moles. And so then this is where things could get a little tricky. So we get 2.4 for our ratio. And we want to try to get it into whole numbers. So what, maybe?
Didn't it say that if it was within 0.1 you can round it? Or I guess that's 2, that's probably not a half round.
Yeah. So, because, yeah, I kind of see, I mean, you could round it to like 2.5 maybe and double it, but yeah, that's a little off. What could you maybe multiply this by that would get you a nice whole number, though? So, yeah, I would multiply it by 5. So 2, if you try to just multiply it by 2, it would still be a little off, right? Because that would only give you 4.8. So again, that's a little awkward. But that's where I say, like, showing your work is going to be super important, right? Because if you can get to here, but then you kind of fudge up the last step, like, I'm going to give a little leniency as long as you can, again, right, show every step, show that you're getting the ratios. Because, yeah, it is kind of a tricky judgment call. But times 5 is probably a little better. So, right, 4 times 5 is 20. So that gives us our 0 here. So I was just kind of thinking about that to try to get us to a whole number. So then we get C5. And then if we do this by 5, that gives us 12. And so that is pretty reasonable for an organic compound. This is way on a side, but a typical alkane formula is Cn, and then the H is 2n plus 2, so that follows. So yeah, that's like pretty reasonable for our formula there. And so this is actually the formula of pentane. Questions on that one? So let's try that process again, basically. Except now we're going to do one that has oxygen. And so we'll figure out a method of how to deal with that. And so I'll just kind of write our reaction setup. So again, we have some unknown compound with carbon, hydrogen, and now oxygen this time. And it produced CO2 and water once again. And so they do give us the initial mass of our sample, so that will be helpful later, but like I said, we'll walk through this. And so our first steps, we can begin the same, right? So just like the same process, let's find moles of CO2 again, right? Just like before, all the carbon gets converted into CO2 anyways. So going through that process, 2.445 grams divided by our molecular weight, which, what did we say it was? About 44.008 or 7 roughly. So 2.445 divided by 44.008. So then we get this many moles, so 0.055. Put enough fives. And so again, this is moles of CO2. There's one atom of carbon in CO2, so that also translates to 0.055 moles of carbon. All right, looking good so far. Now repeat that with water. Again, exact same process like we did in the previous one. So 0.6003 grams of water divided by 18. Forgot what our precise amount was. Let's see, 18.015. Again, you can have small discrepancies with rounding, that's fine. So 0.6003. Excellent. Looks like people have the same answer. So then 0.0333, 2 moles of water. And then just like before, 2 atoms of hydrogen in every 1 molecule of water, so times 2. So 0.06664. So moles of hydrogen now. All right. So now we're here. And so the question is, we need to figure out, right, how much oxygen was in our original sample. But now let's think about what we have. Okay, so we have the total previous mass that we started with, right, our sample that we combusted. We figured out moles of carbon. We figured out moles of hydrogen. So maybe you see where this is going. And so what we want to do is we want to figure out, right, the original mass of oxygen. Right, and this is in our sample, our initial sample. And so again, now we've determined, so I'm just kind of recapping. So we had 0.05555 moles of carbon. And then we also determined that we had 0.06664 moles of hydrogen. And so that means, right, we can translate both of these to mass of carbon and mass of hydrogen, right? Add those up. So then that will give us mass of hydrogen plus carbon, right? Which we can then subtract from our original mass. So let's kind of finish that up. So times 12.011 grams, right? So I'm just converting these moles back to grams. And so I'll do the hydrogen one because that's sitting in my calculator, 0.001. So that gives us 0.067 grams of hydrogen. 6717 or 18. Again, there's going to be minor discrepancies. So let me do it for carbon. So 0.05555 times 12. So about 0.6672 grams from carbon. And so now I'll add, right, our total mass that we have. So again, my mass of carbon plus my mass of hydrogen. So I get about this number. I'll write it down. So 0.73. And again, try not to round until the end here. And so let's subtract that from our original mass, so 0.8233. So minus the mass of our carbon and hydrogen. And so again, this is our mass now of oxygen. Let me just write that out. So find mass of oxygen. So 0.8233 minus the mass that we found. So roughly again 0.0889. So grams of oxygen. And so where do we need to go from here? Do you guess? What's the last step that we need to put everything in the same ratios? So oxygen moles, perfect. So right, we're at the home stretch. So grams to moles. So divide by 15.99 once again. And so now I get 0.005557. So moles of oxygen. All right, good. And so what's the last step again? Once we have all our moles of everything? So formula, so how do we get the formula though? So divide by our smallest, which is now oxygen. So excellent. So divide by smallest moles to get our ratio. So now we have carbon. So that was 0.0555. What do we get? 555 roughly. Divided by 0.05557. So this will come out to roughly 10. I think I dropped a 5. And I mean, that is pretty close, right? So I would just round that to 10 probably. At least I think that's a safe assumption. And so now let's do hydrogen. So again, same process. So 0.06664 divided by our smallest. And, well, that's really close, right? So I put that 12 pretty safely. And then obviously oxygen is 1. And so now we have our formula. And now we can write it out. So C10H12O there. And again, right, just show your work. I'm usually flexible. Again, if there's like minor fluctuations, discrepancies from this amount. But just show your work at every step so I can at least follow that you did the correct process if anything weird happens at the rounding step. Okay. Questions about this process? Feeling good so far? Okay, excellent. So again, ask questions, get help if you don't understand. This will certainly come up on the final. All right, so now we'll keep kind of moving on to a similar topic. So now our stoichiometry, so really writing our balanced equations, and again, just emphasizing how to calculate these really daily calculations, right? So you have to think about, if you're a synthetic chemist, you're in grad school, you know, every single day you're going to be writing, hopefully you'll be setting up several reactions every day. And on the top of your lab notebook, right, is going to be that reaction. What are you doing today? You're going to write out your reaction and then the amounts of it, right? That's super important. That's literally all stoichiometry is about, right? How much materials do I need to go weigh out, right? Do I have enough material? What do I need to do? Like, what am I setting up, right? That's your basic recipe, guidebook, everything for your reaction. And again, we want to just keep practicing putting all these things together. I think we got a good taste of that last week with our reaction lab. But we also want to put the correct symbols. So in this case, right, C8H18, this is referring to octane, and it has an L there to show that octane is a liquid, and we are adding it in a liquid form to this reaction. And again, right, adding an oxygen, which is in our gas state, creating CO2 in a gas state, and water in a gas state. And then, of course, the stoichiometry is also telling us the ratio that everything is in. And so we'll look at, again, how they're balanced by our mole ratio here, but then obviously, right, you want to be able to convert moles to grams, since, again, if you're in lab, right, every single day you got to at least do plenty of reactions and go out, go weigh stuff, go purify stuff, figure out what you need to make that reaction happen and on what scale. And again, just kind of thinking about what this is saying, so we can look at it in terms of molecules, that yes, 2 molecules react with 25 molecules of oxygen to give us 16 molecules of CO2 and 18 molecules of water. Or we have our wonderful mole unit, and this is again where the mole is powerful, is that we have, right, our mole ratios. And so we're saying we have 2 moles of octane reacting with 25 moles of oxygen to form 16 moles of CO2 and 18 moles of water. And so there's our ratio. All right, so let's start looking at this. And so I like to kind of put it in the context of s'mores and like food, because everybody likes food and everybody can do these s'mores stoichiometry pretty well. And again, the whole point of like visualizing this as a s'more is to think about, okay, well now when I'm looking at a mole of water or whatever chemical, right, we can kind of translate the same thing in our brain. And so the first thing we need to do is write out our balanced equation. Again, right, you're in grad school, you got to set up what reaction you're doing that day. Hopefully at least 10 reactions every day. And so then we'll start with our formula. And so we're going to do 2 graham crackers. And then I picked a jumbo marshmallow. And I apologize for my lack of artistic skills. So my cylindrical jumbo marshmallow. And then we'll do 3 mini pieces of Hershey's chocolate. So 1, 2, 3 little bars there. And then that gives us, right, 1 s'more. Again, I apologize for my terrible artistic skills. All right, so now let's do these. And so again, referencing our balanced equation, so if we want to make 10 s'mores, how many pieces of chocolate do you need? So take a minute, and you guys can shout it at me. 30. And so, right, you did this without really thinking about it. Again, it's really easy to think about food and s'mores for some reason in this way. So yeah, you're right, you have 10 s'mores. Okay, we can look at our equation. So 3 chocolate pieces. Maybe we want to actually make some dimensional analysis. Again, so when we're doing this with chemicals, we know what to plug in. And so, right, if we have 10 s'mores, we can plug in our ratio. So from the balanced equation, right, we have 3 chocolate pieces in 1 s'more. So there's our ratio. So then, yes, that's how we got to our 30 chocolates that we need. So, okay, so far so good. Everybody likes s'more math. What about this one? So if we have 32 graham crackers, how many chocolate pieces do I need? And again, y'all can yell it at me or 48. And see, everyone is so wonderful and quick at s'more math.
I'm hungry.
I know, I'm sorry. And so, right, again, we'll go back to our formula. So 32 moles of graham crackers. So you guys were correct, but again, let's just kind of break that down. So looking at our balanced equation, so for every 2 graham crackers, we need 3 pieces of chocolate. So again, y'all did that pretty quickly. So just remember these same things, right? When you're, again, looking at chemicals, there's nothing any different. Just replace your chemical with a marshmallow piece. All right, 3 chocolates. So a little mental math. Yeah, 32 divided by 2, 16 times 3. So 48 chocolates. Good. All right, let's look at another type of problem that we'll see. And so this is kind of a limiting reagent problem. And so now it's saying I have 543 grams of marshmallows. And then I went ahead and defined our molecular weight. So right, obviously you guys know how to find the molecular weight of a compound by adding it up. But I've defined a marshmallow weight as 76 grams per mole. So I'll rewrite that. So our molecular weight of our marshmallow, 76 grams per mole. So given that data, if we have 543 grams of marshmallows, how many s'mores can we make? Assuming we have excess crackers and chocolate there. So take a minute or so to determine that. So then what do we get for this one? What do we have to do? So what are we effectively doing? When you say, like, set it. So what are we trying to find? So you said 543 divided by 76. And then again, right, we're just, because I want you guys to really be thinking about this in your brain, right? So again, you have a pile of marshmallows. You know it's on the scale of 543, but right, to get back to your formula, you have to put that in your mole-mole ratio. So that's all we're doing, right? Finding out our moles. So 543 divided by 76. And so right, that gives us 7.14 moles. And then of course, right, 1-to-1 mole ratio. So for every one marshmallow, we have one s'more. So about 7 s'mores. And again, the whole point is to get back to our mole-mole ratio, right? I always kind of say that, right, our moles is our safe space. So if we don't know kind of what's going on, right, we can always go back to moles, get everything of your moles, then you can go to your mole-mole ratio and get everything from there. So moles is always a good place to be. All right, so try this one. So this is another limiting reagent type question that we'll see with, again, not so friendly chemicals. And so let's figure out how to translate that. So I'll rewrite our molecular weights. So our graham cracker has a molecular weight of 55 grams per mole. We said that our marshmallow was 76 grams per mole, and our chocolate is 15 grams per mole. And so if we have 430 grams of crackers, 375 grams of marshmallows, and 250 grams of chocolate, what is our limiting reagent? And so meaning, right, which will run out first? Again, pretty easy to see with with cooking, I mean, right? So kind of start working through this. How many moles do you have of each of these? What does that mean for your final product? How many s'mores can you make? Which ingredient is consumed first? So probably take a minute or two to work on this. I'll kind of go over it. So what do we find? I kind of sketched out the work, but then what do we get for our answer? So kind of what we want to do, right? You're starting again with your gram amount. And again, right, another way to think about it in context, you're a grad student, you're trying to figure out how much material can you make of your first step. You're just trying to make a ton of it. So, right, you got everything on the scale, and then you got to compare your mole ratios. So that's all we're doing, right? So starting with our mass of graham crackers divided by our molecular weight, and then of course plugging in, right, essentially our conversion factor from our balanced equation. So how many s'mores could we make with 430 grams of graham crackers? What did y'all get?
I got 3.5 and I rounded to 4.
So I heard 3.5 roughly. Is that what other people got? I have to punch this in across. 3.9. So
We count that as a 4?
So roughly 4. Yeah, I mean, s'mores, this is where the s'mores example kind of breaks down. This is hard to make 3.9 s'mores. But yeah, so roughly 3.9 or 4 s'mores. Good. So what do we get for our marshmallows? How many s'mores does that come out to? So about 4.9 s'mores. Again. All right, and then what do we get for the last one? How many s'mores could we make?
About 5.5.
So 5.5 s'mores. All right, so then which one ran out first? Who was our limiting reagent? Graham crackers, so good. So limiting reagent. So again, we can only get 3.9 graham crackers since our graham crackers is going to run out first. So again, right, thinking back to grad school and what could be happening, okay, that gives you, right, your max amount. And then, of course, you just dial down your reagents to the appropriate ratio then. So, okay, using only this amount, that would yield in 3.9 moles of s'mores. How many marshmallows and how many chocolates would you need? So that would be kind of the next step of that calculation. Or figuring out, right, how much is left over then of these other two reagents. All right, we'll probably end there for today, but that's good. So that leaves a lot of time on Thursday to just kind of practice this. So of course we'll practice it with less fun chemicals, but just think about those s'mores, and hopefully the chemicals will be easy. And then, yeah, I wanted to hand back stuff.
Just gotta think about life.
Yeah, you're just like summarizing it.
And then decide the source.
Yeah. Hold on. Alexa.
But I have a lot. It's like I can just chill here as long as I want, I guess.
Alex.
Then that is wrong. Well, either way, it has to be
I have way too many papers. Can I, Alexa, here's it somewhere. Where'd it go? Oh, here it is. Matthew, is he still here? Max. Tyler. Oh. putting
Create a new energy zone with the configuration.
Well, no, we didn't do the papers of it.
Yeah, I think
Yeah.
we're
Did she even work it out? Look at how beautiful that looks.
Damn. You get a smiley face for that?
No. Yeah, you
Yeah,
did.
you did.
Oh.
For sure.
How you guys are good.
By the way, is the test in the blackboard, is that before or after?
I don't currently end.
Okay, so it's on her.
You know, that was
Yeah.
kind of funky.
I think you're doing good though.
I'm annoying myself on this.
Dave.
Yeah, thank you. Yeah, show me some papers, bud.
Sure, I can go for it.
Skylar, will you let me know if there's no class tomorrow? Because there's no announcement right now.
Why would there not be class tomorrow?
I don't know. Just he took his
Oh,
lunch to
right.
dark, so we had no class yesterday.
I didn't know until,
I showed up for class and nobody was there.
Can you hand this to Molly, please?
Thank you.
Dang, how did his wife end up in here? Dave.
I didn't know until I drove all the way out here for.
Why? Only if you're looking for stuff.
What can we do?
Yeah, so there's no announcement right now.
Did you catch that little error that we made on last week's, or the last class, Skylar?
This is quiz 4.
Yeah.
Definitely don't want to drive out there.
I don't care about the papers.
No, my quiz 4 isn't started. I swear I turned it in.
Hopefully today. I'll do it right now.
Do I need to get that? I swear I turned it in.
Good question.
Yeah, same stuff I asked you about.
Shit, oh,
Well,
finish.
actually, I should reread your email.
Oh.
As soon as you walk away, I finish.
What are you doing? Yeah. We're really far behind.
I know,
Like
like,
the
ah.
error that we made on last time?
Oh,
Reaction one?
I don't know if you got that back yet.
Well, we have, I haven't. That's why I copied it.
It starts now and, yeah.
Yeah.
Yeah, basically whenever.
We were
we
talking
wanna
about
do
that.
stuff.
Right.
Loud with you.
Yeah, if you're interested.
That's pretty much what I wrote in my abstract too.
You just talk to me and then eventually we might meet in person. Honestly.
That's me.
Here, passive art. Yeah, as soon as we get Skylar.
Oh, don't you dare take my
Get
pen.
a bunch, like enough people.
I'm gonna
then
walk
we
back
could
to
do
the car and
contact
get
boys and
I
girls
promise
stuff.
that you
So do I have to redo this then?
Probably, I'll look around again.
Maybe I'll dig through my backpack. Maybe
Yeah.
I just didn't turn it in.
Yeah, like that's what I'm kind of assuming happened, and I'll kind of look around
Overwhelmed
too,
by the amount.
but they're green, so.
I thought you were saying I was. I
No,
was like,
you-
I'm sorry.
Yeah.
Am I distracting
I'll
you?
remember
Please
though,
stop.
but, we might need someone, because I don't remember, I think you need 2 officers to officially charter, because you
What'd you get?
wanted to be an officer.
Oh, dude, if you wrote me on Friday, was like,
You're
we're supposed to, what'd you get? Like,
It's not, you don't have to get much.
Heck,
I know you
Just
got
like
it.
wear
Yeah,
the title.
okay.
It's pretty good for not finishing your test.
I'm surprised that you didn't get that. That's real.
But yeah, that'd be great to have more bodies.
I'm like,
It's good. It's
I'm
good.
like glad, okay, I passed, which makes sense. I did feel decently confident on those like last ones, which is mostly great.
Yeah.
But,
Yeah, I wonder what you got. I think I got something wrong with angular momentum because I didn't put it in radians.
I really just like messed up this term really. I like fell behind and I haven't caught up because I'm doing too much. So.
Well, the
Doing
homework
too
for
much typical
yeah.
community college.
Yeah, well, because I'm in a CNA program right now, so I'm doing like 12-hour clinicals at the hospital, and then when I'm not doing that, I have calculus, chemistry, and physics. So I'm like, yeah, I'm doing way too much. So I'm like, normally I've gotten A's on everything, and right now I've been getting first time in college getting C's and stuff, and I'm like, yeah, okay, my grades are dropping. But I think I can power it out, finish up this term. Hopefully I can just really like get into it and get A's on all the finals maybe. And then my fall in terms of years.
yeah, we'll. Oops.